So let's continue this morning session with another mini course by Satoshi Tsujimoto from Kyoto University, who will lecture about extensions of discrete Toda lattices and their applications to box-ball systems.
Okay, thank you so much. And also thanks to the organizer to give a chance to be here. Thank you so much. And also to be attend for all participants. Thanks so much. Today I will talk about this title is extension of discrete Toda lattice and their application to box-and-ball system. This is my talk. And including this talk, I have four talks, and especially the first talk will be devoted to the very elementary level, and also I want to show very how to say by using the some slide and some movie. I want to show what is the BBS and what is the extension of this one. And also, before going to start, I have to introduce my collaborators. Here is Maeda and Kobayashi and Maino. They are collaborator with me rather a long time. And also, some of them I also borrow from their result to this talk. Okay, anyway, I want to show you the today's plan, also further plan. I want to talk about the first part of this contents, table contents. So first, of course, I want to show what is the soliton and also how to express or describe by using the box-and-ball system. And then the box-and-ball system can be derived from the so-called ultra-discretization of discrete system. So I want to describe. And then the most famous one is KDV picture. But the other, there are several ways, but the other great approach is coming from the Toda picture. So this is closely related to the orthogonal polynomial system, and also closely related to the previous talk by Professor Geffman, and also I would say some relationship between them. Anyway, I want to start with this one. Okay. So first, I would like to introduce the solitons and the box-and-ball system. And here is some picture written by Professor Toda and also great, some Japanese painter, great painter, Hokusai. And this is a solitary wave, which was found in some real wave phenomena. And this is at the Scotland, so found by 1934. And also Hokusai introduced this picture almost at the same time. But of course, this is not truly a solitary wave, but it's a kind of, I think that it's a log wave. So suddenly happened great wave which happened at some point or ocean site. And anyway, this is more realistic or close to our target. This is a solitary wave, and this was a rather long beach and shallow water. It happened at some beach, and you can see some solitary. This is a so-called some peak will be preserved along the time evolution system, but some nonlinear interaction will happen in this case. And also, this is a very famous Kodama's result concerning the result from on the KP soliton solutions. So it looks like a wave type solitary wave, and this is a KP equation. And also, this is the other one. You also the soliton is quite it's a solvable model, but still very complicated phenomena or physical phenomena can be described in this way. And also, this is the first equation in this course. This is a KDV. This was first discovered in this context, and KDV will be like shown in this way. And this is a numerical example, numerical simulation of KDV equation. And it's a bit difficult to find out what is a soliton equation. But we can show the more simple manner. And this is solitons, and which has one peaks, and these peaks will be preserved during the time evolutions. And also, this equation known as many number of conserved quantity. In this case, you see the height of soliton is preserved in any cases. I said that the height will be preserved, but under some during the nonlinear interaction, the height will be changed. But before and after, the height will be preserved. This is obvious. And actually, this height corresponding to the system of eigenvalues of this system. So in this sense, under some very complicated interactions, they remember, they know, or they have a memory on the height of peaks. This is the main feature. And also, this is a very big property, that is bigger soliton is higher than lower solitons. And if the bigger soliton are overpassing smaller soliton, this happens after sufficiently large time has happened, then sorting property has been established. And this sorting property can be used in this property is essential in the numerical algorithm, like a QD or some LU algorithm is related to this one.
Sorry, question.
Yes.
When do you say that two solitons are interacting? When the support of them are not disjoint? Is it?
Yeah, actually, in this case, already some interactions happened, but it's invisible because of the very, very small, almost neglectable. And especially in this is a numerical simulation, so we can neglect, or we can small value will be just disappeared in this information. But basically, it's still some interaction has happened. So this is the continuous system or discrete system. But after that, later I can show the box-and-ball system. This is completely localized, so no interaction happen. Just a very short time interaction happen. Okay, thank you so much. Yes, and also later, I will show this KDV equation, how to analyze this KDV equation. So this is a very classical way to understand this KDV equation. And this is nonlinear equation. And after applying this rational type of transformation, or second derivative log tau, which leads to the Hirota's bilinear equation. And Hirota's bilinear equation is rather easy to deal or to consider the exact solutions. And this Hirota's equation can be discretized in this way. So some bilinear property is preserved after or before this discretization procedure. And after getting this discrete bilinear equation, we can consider the inverse transformation of this rational transformation. This is the discrete analog of second derivative of log tau. And then we obtain the discrete KDV equation. So this is the very classical procedure to obtain this discrete analog KDV equation from this one. But of course, this procedure, this route is not unique. So we can obtain the other type of discrete analog KDV equation. But anyway, this is done by very big, very long time ago. So Hirota has just introduced this way of procedure to derive this one. And then, so very discrete equation has been introduced by Hirota in 1970s, the end of 70s. But this box number is rather recent, but still already 30 years before. So in 1990, Takahashi and Satsuma introduced this box number system as from the heaven at the time. So that is soliton cellular automaton. So which means that cellular automaton describe the previously I showing this soliton property, soliton interactions, and it means that particle preserving and type reversible, and also behave like a particle in terms of in this cellular automata system. So just showing. So maybe many people know about this one, but I just for the unknown people, so I want to show what is the rule of boxable system. And this is very easy. So if the only one consecutive ones has happened, then this is just time evolution is quite easy because we want to describe the soliton properties. So the solitary wave just move to the one to the left from here, in this case, left to the right with this speed. So this, and this is, so just saying about the rule is just pick up the leftmost ball from this binary box, leftmost box, ball, and taken away, and then move to the nearest neighbor empty box. So this is ball coded here to here to here. And in this sense, box and ball system can be described by using, in terms of this very simple rules. So this is size 3 soliton moves with speed 3. Yes. And more complicated case, this is the example. So the rule is same. Pick up the leftmost ball and to move to the nearest one. And then second one, move to the also nearest empty box. But in this case, this first empty box has been already occupied by previous one. So you see, in this picture, we can see some shape of or length of solitons. So here, consecutive ones. I say that this is one soliton. This is another soliton. This is third solitons. And you see the length will be changed. But before and after, the same size of consecutive ones has happened. Yes. Sorry. Yeah.
Sorry, could you explain the dynamics from the third row to the fourth row?
This one?
No, from the third row, yeah.
Okay, third row to the
fourth row. Yes. How do you, what is the precise dynamics?
Okay, maybe the precise, so the, this is more,
okay, you're explaining.
More explicit rule.
Okay,
so,
thank you.
Yeah. So actually, there are several ways to describe this rule. This is actually, this is so-called 1-0 arc rules. And this is more precise in mathematically. And just first pick up the 1-0 subsequence from this binary sequence. Here, so I say that the ball occupied some ball. I say that this is 1, and this is an empty box. I said 0. So this is 1 and 0 is appear here. So as a subsequence. So in this subsequence, this binary sequence, we have 1-0 pattern will be 3 patterns. We have found out 3 cases, 1-0s. So I connect 0 to 1 with arrows. So this is a 1-0 arc. And then next one is also connect the 0 to 1. But in this case, the already connected 1 and 0 should be removed from this system. Then in this case, this is also 2 cases. And also this one is already nothing, so nothing to do. And then this procedure can be continued like this one. And you see, so this one is disappear from the second level, doesn't continue. But anyway, after connecting this 1 and 0, then between, all ones happen, nothing to do. So sorry, maybe I can say the other example, but after connecting all balls to the all balls, then just exchange all the connected ones, 1 and 0s. So you see connected 1 and empty box, just changing the position of balls like this. And then finally we obtain the time operation step has completed with this one. And from this rule, we can say that number of balls are preserved, so particle preserving system. And also, it is obvious that if the time reversibility is also apparent, because after making this, after getting t equal 1 binary sequence, we will consider the, if we consider the 0-1 arc, so 0-1 arc, 0-1 arc, 0 arc, so this reverse procedure is clear, and it means that the time reversible system from this is visible. Here, and also I want to stress this is a conserved quantity is quite important, and you see this connected arc 0-1 arc, or this is 1-0 arc. So in each step we counting up the how many 1-0 arc has happened. So first level, first arc line is on 3, and second arc line is 2, and then 1-1-1 is happened. And this is actually this shape of diagram are preserved. So let's check the one more time evolution. So this is time t equal 1. Then we can consider the same procedure to this binary sequence. And 3 arc lines happened, and the other one is also second one. 3, 1, 1. And complete, so the first, the time equal, t equal 0 binary sequence, and also t equal 1 case, only 2 examples, but we have checked that this is, it might be a conserved property has happened. And moreover, this conserved quantity describes the contents of solitons. So you see, this is in this state, t equal 1 state, consecutive ones has 3 consecutive ones, and size is 2 to 4. But you see, this by starting from this situation, we can figure out the soliton contents of solitons. So here, after this is under the interactions. After finishing these interactions, we obtain the solitons, which we will not already interaction has completed. So here 1, 2, 5. So if we consider the transpose of these diagrams, so 1, 2, 3, 4, 5, 2, 5, 2, 1. This is just coincide with the contents of solitons. So this is happened. Okay, sorry. Yeah. Question?
Do you call the biggest arc SLNs 5? Like.
Sorry, this one?
Yeah.
Yes, this is the last one is 5. The level of, so in each procedure we count how many arc can be produced. So is it okay? So
So this is just a gradation, it's not a number, how many cells we...
1, 2, 3, 4, 5. This is, yeah, 5.
Thanks. The number of cells is not like 5 or 10 between two...
No, it's not the numbers.
Yeah.
It's the number of arcs below.
Yeah, okay, thanks.
Yeah. Yes. Okay.
What was the question?
Yes.
What was the question?
You didn't understand the question. Could you repeat it?
Oh, yeah. I mean that, so this is fifth arc means the level of step. Each step, the first procedure, and second procedure, third procedure, each procedure, we count up how many 0, 1 or 1, 0 arc has appeared. So then the last one is the fifth one, and the fifth one leads to the only 1 arcs. I think you got, yeah. Maybe it's not so difficult, very elementary concept.
Sorry, you will prove all these theorems, or?
Yes, of course.
Later on.
Sure.
Okay.
Not in this talk, but this is
Later.
very important procedure.
Thanks.
Okay.
So these arcs also identify with non-crossing partitions, right?
Yeah, it's a partition, really, this is, how to say. So
you identify these arcs with these tableaus, young tableaus, right?
Young tableau, yes.
And so for the previous, the non-crossing partitions that we get in the previous step, did you find any similarities between the non-crossing partitions for the pictures?
You mean this? So what I told you. Yes.
From t is equal to 0 when you move to t is equal to 1. So are the shapes same or?
Yes, same.
Oh, yeah. Exactly same.
This is the main point. And before and after, so or in each step, this diagram, so my Young diagram will be preserved. This is a theorem. And yes.
Only unidirectional hopping, is it a rule or like only in one direction particle?
Only one direction.
It's a rule.
This is the rule, yes.
Okay, and you are considering open boundary condition on the chain? Or?
Yeah, actually, yeah, of course. I have to more strictly, better to define. So I consider the semi-infinite number of box, and I put the finite number of balls only in this case. Yeah, of course, it's possible to extend to the double-sided, double infinite lattice, and also we can introduce we can put the infinite number of boxes from left and right. But in my talk, I restricted to the finite semi-infinite box, and each box can contain only 1 balls, and a finite number of balls. This is the restriction under my talk. So this is the way. Okay. Yes. Yeah. Yes. Maybe better to say as a related topic. So this box and ball system can be related to the so-called Pitman transformation in the probabilistic interpretation. So Pitman transformation is famous in the class in the probabilistic probability theory, and we have already explained how to relate with this model and this Pitman transformation. But in this talk, I just skip all detail in these topics. But this is also very important and also interesting for further research. Anyway, I would like to proceed my talk. And here, just summarize the property of a box sample system. So soliton cellular automaton, which should behave like particle and do not change the size of before and after. Also, some nonlinear interaction has happened. And the sorting property will be essential to consider some numerical algorithm. And this is a very simple example. And this is a first model of this soliton cellular automata system. And we can generalize or extend this box sample system to the more complicated or more additional rule can be added to this model. Yes, okay. And okay.
A question about the previous slide. When you say the phases are changed, this is when you have several balls per box, or
yes.
When there's one ball only, you have a difference of phase?
So you see the phase shift has happened. So this is the one only length one soliton. So this is the speed is only one, and after interaction, this size one soliton will be shifted to the backward. But on the other hand, this bigger soliton is a bigger soliton can slightly shift forward. So this is a nonlinear interaction, usually a soliton property. Soliton phenomena will be wave propagation will be this happen.
So by phase you mean like location in the global system?
Yes.
Not some internal phase of the
internal phase should be fixed, I think, but in the appearance in the nonlinear level, this such nonlinear some shift will be happen. Yeah. Okay, sorry. Yes, on the previously I explained by using the 0-1 arc or 1-0 arc, but actually there's another way of describing this rule, so-called the carrier rule. And the carrier rule is we consider some carrier running from the left to the right, and this is the rule of carrier. So if the carrier is in some sense, very simple. If the carrier, just the first initial state of carrier is maybe no ball are loaded on the carrier. But if the carrier appear with the ball, then just load it to the carrier. And just put on the ball to the carrier. Up to the carrier, up, and then after carrier move up, meet with on this empty box, then this already 5 ball has loaded to the carrier at this state. At this, the carrier unloads the ball to the empty box. So it means that we can pick up the ball up, and down. After 5 balls down, then carrier has no ball, empty. So here, nothing to do. Then move to the left, to the nearest next balls, and then pick up, down, up, down. So this is then after that, carrier just go passing, nothing to do. Then by using this rule, it's also we can obtain the same time evolution diagram from 0 to 6 in this way. And this carrier, so we can introduce the carrier rule with some additional restriction, like carrier capacity. The original Takahashi-Satsuma rule has no restriction on the number, how many number of balls can be loaded to the carrier. So the original one is infinitely many number of balls can be loaded, but we can introduce the carrier capacity. So if the carrier capacity is finite, then the speed, the soliton speed will be limited. So this is the time evolution rule after introducing this carrier capacity. So if in this case, I put the carrier capacity is equal to 4. So it means that if the carrier loaded 4 balls, then next meet with this ball, then, but already maximum capacity has happened, so nothing, so it's impossible to load, or even unload also impossible. So just move to the left, so nothing. So in this sense, this 5 ball will be shifted with speed 4. So this is a different time evolution with previous example, so original box and ball system. So like this one, so this is a very fast level of generalization of extension of box and ball system. But here we have many kind of extensions. So box capacity is firstly introduced by Takahashi himself. And also carrier capacity is this slightly later, so, but also Takahashi's Matsuki-Daira. And this carrier capacity can be changed with, so sorry, this is not named. So carrier capacity can be changed in each time step. We can change. Even in such a manner, we can describe the exact solution. So this is integrable system. And also, we only consider the one kind of ball in Takahashi-Satsuma system. And also, box also only one kind of box. But here, we can introduce many kind of balls. So colored ball means red ball and blue ball and black ball. So each ball, slightly different rule can be applied to this. Also, box, so here, box is a box, usually. But in this, some extension, so Yamamoto et al. Has introduced the box slightly changed. So blue box, red box, yellow box, different this rule has been introduced. Even such rather complicated rule, we can say this is integrable system. And you know, also, of course, some new rule has been introduced by using some root system. Of course, I also in my talk, I don't say about quantum analog or Q to the 0 limit or crystal limit of this model, but by using this crystal basis, the theorem, some new rule has been introduced, B type, C type, D type, and so on. And here, we just restricted the initial value is taken only 0 and 1. 0 or 1 means, yes, this is, if we consider the ball, this is integer, should be integer. But we don't care about it's a ball or not. So in this case, we can introduce the real value or even negative value can be chosen. So in this case, slightly different. And first, maybe negative value can introduced by Hirota. So, and after that, some great effort to understanding this negative soliton and real value solitons. So, sorry, I forgot. So Professor Willox has introduced how to understand this negative soliton and the real value solitons in more general setting, and they can introduce some how to solve. It's a kind of ultra-discrete analog inverse scattering method. This is also great work. Yes, also there are many. But in this talk, I want to introduce some analog of corresponding box number system. So starting from relative Toda lattice and elementary Toda orbits and R1 chain. And I want to point it out that this elementary Toda orbits has first introduced by Professor Keftan and also favorable speech in 2000. So this is also, this talk, maybe I want to consider what is if we start from these systems, what kind of box and ball system has been arrived in this sense. Okay.
So it seems like virtually any generalization you do, you can get solitons. But do you know, I mean, is it that, do you know examples where it does not have this soliton property? I mean, can you, is there, I mean,
okay.
At what level does it break down? I mean, does everything work? I mean,
yes, but yeah, I can't say that if we restrict the initial value taken from 0 or 1, in this, for example, original box and ball system, all phenomena can be decomposed with only solitons, no other solutions. But if we allow to introduce the negative value or some negative values, in this case, not only the soliton will be happen. It's a more complicated situation. But anyway, all of these has some soliton property if we at least if we restrict some initial range of initial values. It is. And the box and ball system is coming from our soliton solutions, soliton system, but it is related to the many fields. Like, of course, this is a original one, so integral system can be considered from this one. We obtain the box and ball system, but analysis or application, also a polynomial system or numerical algorithm, and also several automaton. Of course, this is some application, and also combinatorics and probability will be closely related. And so probability is so you maybe better to say that Pitman transformation is closely related. Anyway, I want to extend this box and ball system and also how to relate with what kind of fields. Or we want to extend this box and ball system to the more wider area. Yes, and then, yeah. Okay, this is just a very beginning of this one. So we start from the soliton in terms of, we start from the nonlinear partial differential equation as a KdV equation. But it's better to start from the discrete integrable system. So this is the discrete KdV equation, and it's easy to consider derive the KdV equation by using some continuous limit. And okay.
So from KdV equation, that is, we can transform to Hirota bilinear equation, right?
Yes.
So from Hirota bilinear equation, you are making this a discrete KdV equation.
Yes,
so
yes.
Is it right to say that any model which has Hirota bilinear formalism, we can get a discrete counterpart of that?
Sorry,
so we have KdV equation, which is transformed to this Hirota bilinear version of that.
Yes.
So is it right to say that any Hirota bilinear equation can be transformed? From that we can get a discrete version of that model. So like how you are getting from KdV, you are getting discrete KdV using Hirota bilinear equation, correct?
Yes, of course. Now it's not so. By starting from the discrete bilinear continuous bilinear equation, we can obtain the corresponding discrete analog, the discrete bilinear form possible to derive. But first, this is not unique. Several kind of discrete analogs exist. And also, if we obtain the some corresponding discrete analog of bilinear equation, we should consider the inverse transformation to the nonlinear equation to obtain the nonlinear equation like this. So this transformation also not so unique.
Okay.
Yeah, and also the main point is how to discretize the continuous bilinear equation to the discrete one. Okay. So, but it's better to consider the inverse problem. So I mean, if start from the discrete version of bilinear equation So later, I just in my talk, I
Thank you, sir.
say, but this is not so trivial. But now it's already established some way to how to do that. Anyway, this is a KDV equation, and so continuous limit itself, it's not so trivial. So we have this is a discrete KDV equation, very famous one, and when we want to consider the continuous limit, we have to. This is one choice. By introducing this type of transformation. So epsilon is a small parameter, and delta. So this is delta is corresponding to the time intervals. So delta should be epsilon cubic should be, and after introducing this independent variable transformation, we obtained the KDV equation. And okay, chat. So, and discrete analog can give us a discrete how to simulate the original KDV equation in terms of KDV equation like this one. It's quite a stable equation. Yeah, it's okay. Ultra discrete. So our main target is how to introduce or how to understand this ultra discrete system from the discrete integrable system. So the main key point is ultra discrete limit, which was introduced by Tokio, Takahashi, Matsuda, Sasuma in 1996. And this is very, very well known. And the target is previously discrete system is only considered discretize the independent variable space or time. But in this procedure, we also discretize the dependent variable dependent variables. So all of them should be integer. And how to do this ultra discrete limit is just taking this type of variable dependent variable transformation and also take some limit. And by using this ultra discretion, if we start from some rational map, we can obtain piecewise linear system, which has a dynamic system that maps an integer sequence to the integer sequence, which will give us a good example of this ultra discrete system. And usually, piecewise linear system can map the integer initial values to the integers. So they will close under the integer. But we want more restriction. We want to consider the more restricted system. So we want to consider only the finite number of dependent variables. So this is a cellular automata system. If we can restrict only 0 or 1, a binary sequence maps to the binary sequence, this gives us a cellular automata system. And okay, yes. Okay, sure.
So this is like what's it called? This max plus algebra? Is that what?
Yes.
This is
it's
tropical.
Yeah.
Algebra.
It's a tropical limit, but yes. So procedure is slightly different, but result almost all, not all, but almost all results should be coincide.
Okay.
And also tropical tropical geometry and ultra discretization has been almost same time they discovered. Yeah.
Sorry, what did you say that the procedure is slightly different between tropical and ultra discrete?
Yes. So tropical limit more formal, as far as I understood. So, for example, more to say this is a next slide. So usually tropical geometry, if minus constant happened, they will just don't care about plus or minus. So like determinant can be, so by using tropical limit, it's possible to consider the corresponding one. It's a kind of, yeah, it's slightly different in my mind. Anyways, this is the ultra-disc limit. It's more concrete. And I want to say that the positivity of, in this ultra-discrete limit, the positivity is essential. And you see, this is already, I show you the exponential A plus exponential B should be max A comma B. But if this plus sign could be minus sign, and also B is bigger than A. In this case, you see this, the first term will be lower, less than second term as a sign. So, but logarithm minus is not unique, and also beyond the real value. It's we want to consider the binary sequence to the binary sequence. In this sense, in this case, if this situation happened, some not good situation happened. So we call the problem of subtraction. So, for example, in our discrete KDB, as a final step, we achieve the corresponding box-and-borrow system. Just starting from this system, we can obtain. But at the first glance, discrete KDB equation should compute this minus sign. So subtraction should be avoidable. Yes, but yes, I can. Yeah, in order to compute this one, we need to be, usually, we think that it should be, we have to compute the minus sign. So, but of course, first, at this moment, we can say rational mapping without subtraction is preferable when we consider the ultra-discrete limit. This is a preference. But as somebody already considering, it's possible to take an ultra-discrete limit, even if considering if appear this minus sign exists. I mean that all negative terms should be transported to the other side, which will destroy, remove the minus sign. It's possible to take a, yes, really, it's possible to take a ultra-discrete limit. So you see, so of course, one is exponential 0. So we took, so 1 as a 0. And the negative, so division should be replaced with minus operation. And you will just here. And plus is just, two terms will be connected with max. And equal max. So in this, it's possible, this is a ultra-discretization of discrete KD equation. Is it? Yeah, it's not, because if we want to compute this value, u, but at some case, it's possible to compute. But if this second term will be greater than this one, then this information will be disappeared. So it's impossible to uniquely determine. We want to determine this value, but in this case, it's impossible. So the how to overcome these difficulties? This is introduction of good or positive auxiliary variable. So-called here we say C. And okay, just later we can say why we can choose this variable. But in this case, if we introduce this new dependent variable C, and actually by using this discrete KDB equation, C can be rewritten in this way. So just one-time application of the original discrete KDB equation. And this one can be, is also a very simple calculation. And so we just put forward like just rewritten in this way, and you can observe that this term will be just shifting with this term by n to the n minus 1. So here, Cn plus 1 is equal to u over u times C Tn. This is no negative sign or subtraction up here. And also, we have definition of ut, just this definition can be rewritten in this way. Here, definition can be written in this way, and the second equation is just we compute it. And okay, of course, we have to put the C and T as a boundary condition. We have to add one more boundary condition information. But by putting this additional boundary condition, we can easily obtain this, we can calculate this UNT plus 1 without using the subtraction. Then, okay, it's easy to already, now we can apply this ultra-discrete limit like this one. So here I I can say UNT will be go up to the exponential, C also, delta also. And by making use of the ultra-discrete limit, we obtain the piecewise linear equation from this one. Because delta inverse is coming to the 1, and divided means the minus sign, and denominator term will be max u comma c, and this one. And then, yeah, for later use, with slight variable transformation we introduced. Then this is a standard form of ultra-discrete limit, ultra-discrete KdV equation, starting from the KdV equation. And actually, this ultra-discrete KdV equation or ultra-discrete KdV lattice can be interpreted in terms of box number as this ultra-discrete KdV lattice describes our original box number system. It's a very surprising result. And how to interpret this value? So eta n is, of course, we start from the binary sequence. As I said that we consider the semi-infinite integer lattice, and each site we have 0 or 1, so binary sequence. So the first letter should be 1 or 0 or 1, so I denoted by eta 0, eta 1, eta 2. This is a 0, 1, 0, 1, 0, 1, so this is a binary sequence. And Wn means this is a carrier rule. And the Wnt denotes the number of balls placed in the carrier at n. So, of course, at this moment, we don't know about this system describes the box number system or even a serial automaton or not. And we have some theorem that this system, if we start from the binary sequence, we can transform the other binary sequence as a one-step time evolution. So this is a theorem. So, and also this is a boundary condition. Actually, already we know about this system is just coincide with box number system. So in this case, W minus 1 is a carrier from the left-hand side. So at the left boundary, carrier does not have any number of balls. So we can start from 0 or 1 or 2 or 3. This is a boundary condition. We can consider not only the 0 as a boundaries. And it is easy to prove this theorem. So we start from eta k is 0 or 1, or wk minus is positive 1. But if we assume this condition, then eta k, the term relation is coming from this one, and just plug in this definition of Wn, like this one. And then we obtain this type of expression. So in this at the final stage, we introduce this very famous min-max relation formula. So this is very clear. And by using this one, so we start from eta k is 0 or 1, and wk minus 1 is bigger than 0 or 1. So wk minus 1 is non-negative value, non-negative integer. So eta k is 0 or 1 means you see this wk should be positive value. And this is a proof of this theorem. And in this way, we can obtain this from the KDB discrete, ultra-discrete analog of KDB equation can describe the Box-Ambor system. But this is one very famous, one possible representation, so-called Euler representation. And also, we have also another description on this Box-Ambor system, so-called finite Toda representations. And finite Toda representation means we consider the discrete, ultra-discrete analog of Toda equation, which can describe the Box-Ambor system. So maybe it's not. And but if so, someone already well known that discrete Toda equation usually like written in this way. Maybe this one also later I can show how to introduce this equation. But anyway, in this case also we have negative sign originally, but this discrete Toda is related to the numerical algorithm, like so-called QD algorithm. So QD means the quotient difference algorithm, and which has subtraction procedure. But it's possible to this negative sign is not good in numerical algorithm because of the negative. So subtraction causes some drop of significant digits, which will not preferable in numerical simulation. So already in numerical algorithm, already introduced this QD algorithm can be described without using subtraction, so-called differential QD algorithm, which was also already introduced in the field of numerical algorithm. So after introducing this this equation to the without subtraction free form, which was numerically stable and also possible to compute with keeping the higher precision numeric computations has happened. So in this sense, in numerical system, this subtraction free form is very preferable from this sense. And also in our integrable system, subtraction free form also preferable. It's possible to apply the ultra-discrete limit to this system. Okay, so QD algorithm is like this one. So just I ought to say. And QD algorithm is given like this one. So this is this is Jacobi matrix, which has appeared in the Professor Gefman's talk. And it's if we assuming some possibility we decompose into the bidiagonal matrix, two bidiagonal. One is lower, and the other one is upper diagonal, bidiagonal one. And so this after decompose into the two bidiagonal matrices. After that, we exchange the order of matrices. So this is the time evolution. So A0 is the original first our three-diagonal matrix, and then decompose into bidiagonal matrix and exchange. So LR to the RL. And then this is, we can define the new three-diagonal matrix. It's a time evolution step. So repeated, we obtain the, after some sufficiently many repeated number, we obtain the eigenvalues of this Jacobi matrix.
So it will become a diagonal?
Yeah, upper diagonal, upper triangle matrix. Yeah, because you see, the A0 can be 0, but this 1 should be remains. Okay. And then this will give us a discrete Toda equation. And if A0 has this type of eigenvalues, which will lead to the each Q0, Q1, Q2 goes to the eigenvalues from the order. So this is the sorting property. And yes, this is closely related to the Jacobi matrix, which was appeared in the previous one. And also, the previous one is introduced by the, I just forgot to do it. Sorry, I just say that in 1960, Ritz-Hauser introduced this algorithm. But this, in 1994, Fernando Pallet has introduced the some subtraction free form of this QD algorithm, even the shifted one. But here you see this algorithm contains a subtraction. But after introducing this time-dependent variable, this discrete totalities can be rewritten in this way that this is very preferable in numerical algorithm sense. And it's possible to apply the ultra discretization. So I want to skip this slide, but just a similar trick has applied to this loop model. And then we obtain if we obtain this type of expression, we can easily to apply the ultra discretization model. This is the final state. This is the ultra discrete Toda lattice. I want to explain how to understand this Toda system can describe the original box-level system. So this is our ultra discrete Toda lattice, and by using this, we assuming this boundary condition upon left-hand side and right-hand side in E, and Q denotes the number of balls of the nth block at time t. So slightly, please compare with the KDB picture. So in this Toda picture, Q0 denotes the how many number of consecutive ones has happened at in each blocks. So here, first block, second block, third block, and each of them 5, 4, 2. So 5, 4, 2 for Q0, Q1, Q2, and E denotes the how many number of empty boxes between ones and consecutive ones. So here is 1, 2, 3, 4, 5, 4, 5, 3. So 5, 3 is just we put, and then we calculate by using this ultra discrete system with Toda, and then we obtain this sequence. And this sequence just coincides with same understanding for each binary step. But of course, here we have to consider some, or we have to compute the additional value with how many number of zeros before first one's block. But it's not so easy, but it's not so difficult, quite easy. And, from this sense, from this Toda representation, E minus 1 means how many number of zeros in the left-hand side. So basically, this is infinitely many number, 0 has continuum. So in this sense, we have to put one more direction, one more additional computation equation. We obtain the completely same box-level system by using this Toda ultra discrete Toda. And you see that we just saying the KDB goes to the box-level system as solitons. But in this case, in Toda picture, we have to consider the finitely many number of systems. This is in the integrable system, the corresponding exact solution is quite a completely different manner. So in soliton, we can consider the infinitely many integer lattices as a space. But in case of Toda case, finitely many. So it means that the size of a matrix is finite. And finite size of three-diagonal matrix can be related to this system. So yeah, so maybe already time has come, and I want to stop here. But in the later, the second talk, or the further talk, we want to focus on this system, and especially solution of finite lattice. And this solution can be analyzed by using the theory of orthogonal polynomial. So next slide, next talk as a problem, I want to introduce the elementary introduction to the orthogonal polynomial, which will be very useful to consider the corresponding solution of this one. And actually, it is closely related to the, it's a totally non-negative or totally non-negative matrix can be very useful to understanding this system. So this is for next talk, my plan. Yes. Thank you so much.
Thank you very much for this lecture. We now have several minutes for questions.
The discrete KdV to KdV equation, in which functional space does it hold? For instance, does it hold, is the convergence, does the convergence hold uniformly on complex subsets or something like that?
Actually, I can't get your question, so.
Convergence.
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 It's
So
mean
when you rescale the discrete KdV equation, you get some equation that depends on some function that depends on epsilon, and also some time t and time x. So I understand that for every t and x, as epsilon goes to 0, my discrete KdV solution converges to a solution to KdV.
yes.
But can we say more than for each t and x?
More precise convergence.
Yes.
Actually, I don't know the answer to the answer, but yeah, it's possible to consider in each step we can introduce this epsilon and some expansion with respect to some small values. It's possible to do. Maybe some inequality can be done. Okay. Yeah.
Thank you. I have another one. So you said that box-ball systems, the update is related to a Pitman transform. For discrete KdV, is it related to the geometric Pitman transform?
Yes, I think, yes. I think so. Already, so yeah, my collaborator has been published several papers, I think.
Sorry, who?
Collaborator has published corresponding result on these topics.
Thank you.
Do you call something as integrability for ultra-discrete case? Like,
yeah. In this case, it's possible to solve some initial value problem.
I understand integrability for discrete case, for example, when you have some cluster coordinates as just a Poisson system and integrals. But here, is it different or it's?
This is more clear that in any initial value. So here if we restrict, there are several versions, but if we restrict any binary sequence, if we start, we can compute in each step as a closed form, as a solutions. So it's possible to solve the initial value problem. Of course, some boundaries.
But do you have some commutative flows or?
Sorry?
Commutative flows like some Poisson structure, like in a naive way?
Yeah. Do you know, Rav-san? Yeah, I think so, yes.
Yes, I don't want to interrupt your question, but I actually had something that is related to your question. I had a comment on the last slide.
Yeah.
Because, well, Tsujimoto-san knows I'm a very big fan of the KdV equation, well, the ultra-discrete KdV equation. But actually the Toda lattice system, in a sense, is much more versatile than the KdV equation. Because as Tsujimoto-san pointed out very correctly, if you try to figure out what happens to the box and ball system on a finite lattice, so really with sharp cutoffs at the edges, then the KdV equation won't do the job. You can't do the analysis.
Yeah.
KdV only works on the half lattice or the full lattice. The way the Toda lattice was introduced here was specific to the finite lattice case. But of course, there is the infinite lattice case or the half lattice Toda equation as well. Of course, the mathematics behind the evolutions and behind for example, if you would try to solve the Cauchy problems, the mathematics behind all these systems are different, but the same equation actually holds. So in that sense, the Toda lattice is much more versatile. Now, there is another thing going on. There is actually a reinterpretation of the ultra-discrete KdV equation in terms of the infinite lattice Toda lattice. And both descriptions, it's easy to see that they're equivalent. Now, Takagi-san, maybe 10 years ago, actually came up with a very clever construction of commuting flows for the infinite lattice Toda equation. So basically, it's a tropical version of the Toda lattice hierarchy. And so he actually shows that there are infinitely many commuting flows for the infinite lattice case.
And this is ultra-discrete, it's in accordance with the ultra-discrete.
And that is completely equivalent to the ultra-discrete KdV equation. But if you try to do that on the ultra-discrete KdV equation, I have no idea how you would do that, actually. Yes.
Thanks.
To be honest, I never thought about it because it's been done. So I don't know if there's anything to be gained from doing it for completely in the ultra KdV setting. Maybe it can be done, but I don't know. That's
Yeah.
what I want to say, actually.
So I got a bit lost in your Toda lattice story. So is my understanding correct that the dynamics here is the same as the KdV dynamics?
It is.
There's absolutely no difference.
Yes, no difference.
But you somehow restrict, then you restrict the size of the lattice to n, which was the size of your original matrix.
Yeah,
Right.
it's of course corresponding dynamical system should be changed, should be modified if you introduce a speed limit.
Which speed? Sorry.
It's if you restrict you mean the speed limit?
No, I mean.
No?
No, I don't know what you mean by
Sorry,
speed limit.
yeah.
Sorry, I was just, you started with a n by n matrix, right? Jacobi matrix.
Yes,
And then you had this dynamical system.
yes.
From there, you derived this using some bunch of steps, right? But the dynamics is the same as the KdV dynamics, except that you restrict to a finite lattice, right?
Final lattice means on the Toda lattice level. But box and ball system has a semi-infinite number of lattice.
But I'm confused. I thought you said that this has to be finite.
Yeah. Sorry.
Yeah.
So when you use the viewpoint of total lattice with finite size, this size depends on the number of solitons in
Yes.
this system.
You see,
Yes. So
This is-
the number of soliton
Yes.
is the number, the size of total lattice in this talk.
But what is the size of the matrix doing then?
So the size of
This is
size
3 by
of
3.
two-diagonal matrix.
3 by 3, 3 diagonal matrices.
Yeah.
Yes, 3.
3, 4, Q0, Q1. Yeah.
So
N by n. So if you have n by n
Yes.
three-diagonal matrix
Yes.
for total lattice,
yes,
then you have n minus 1 or n solitons in
Oh, it's the number of solitons.
Yes,
That
yes.
is not the size of the lattice.
No, no.
Yes.
It is a point. So if you know the number of solitons in this system,
Yes.
then you can transform this system related to discrete KDV to discrete Toda with finite size.
Okay.
So if the number of solitons is different, then the size of Toda is different.
I see.
Yeah.
Yes.
Okay.
Yeah.
But there is another piece of information here which was not there in the KDV, which is this E1, E0, E1.
E0, E1.
Yeah, that was not there in the KDV.
Yeah,
setting.
no. KDB also know about this information.
No, it knows, of course, because there's everything, all the information is contained. But what is the statement here about, I mean, I guess I don't understand why you are stressing the E0, E1. This was there earlier also, right? In the KDV setting also you knew how many spaces are there between the adjacent blocks.
In the initial binary sequence.
Right.
Yes.
But you did not stress that when you were discussing KDV. But now you are stressing this.
Yeah, I see. Yes.
What is the why? I mean, no, it is implicit. I mean, is it because in your Toda system somehow this comes up and it did not come up in the KDV system? Is that what it is?
Are you saying about the transformation between the view of discrete KDV and KDV and Toda? So if we have some configuration in ultra discrete KDV, and you can know the coordinate in ultra discrete Toda lattice from U to Q and E. And but we can reverse this map. The inverse map is possible if you know how many zeros or empty box in the left side.
Yes.
Then if you know this number, and you can inverse this map from discrete Toda to the discrete KDV. So this is what Tsujimoto-san said. So if you know the number of empty box in the left side, then you can make inverse map. Otherwise, it's not possible.
Okay.
Yeah.
I see. Okay. Thank you.
Thank you so much.
Any further questions? If not, let's thank Tsujimoto-san again.